All right, Chemistry 3101. So we left off at problem 8.31, and it says predict the products of each of the following reactions. I mean, each one of these is a syn dihydroxylation. However, it says in each case, make sure to consider the number of chiral centers being formed. So for the first one, so for A, in A, we end up with our skeleton like this. We have one hydroxyl going up, and then we have the other hydroxyl group going up, right? You always write the skeleton in the same way that it's written because we're starting it with a trans alkene. And so we have to keep that zigzag pattern like this. One hydroxyl is going up and the other hydroxyl is going up. But the question is this a meso compound? Could anybody answer that? I'll put here meso question mark. Is this a meso, yes or no? Does anybody have an idea about this compound? Is that a meso compound or not a meso? Thanks, Jenny. You're absolutely right. It is not a meso compound, right? Because if we rotate this carbon-carbon bond, we see that we draw the compound like this. We have one hydroxyl pointing up and the other hydroxyl is pointing down. So that means that we're also going to get the compound where we switch both of those wedges and dashes. And so that means we end up with a pair of enantiomers for A. All right, let's try B. So in B, I'll just put it down here. So here is our 3 carbons. We're going to have one hydroxyl group pointing up, and I'll draw the other one pointing up. Okay, but what do you notice about this structure? There's nothing technically wrong with what I've written down here, but there are no stereocenters in this compound. Okay, actually, sorry, there is one stereocenter in the compound. This is a stereocenter. So we'll just put here one stereocenter, which is this one here. So one stereocenter. So I think a better way to draw the compound would be like this, and then put the one hydroxyl that's on the stereocenter going up, and then just write plus the enantiomer as well. And then for C, in C, we end up with our cyclohexane ring. We have one hydroxyl group pointing up and one hydroxyl group pointing up, right? Because this is a syn dihydroxylation. Am I going to get an enantiomer in this case? Yes or no? Exactly. There's going to be no enantiomer in this case. Why? Because this is what type of compound? Excuse me. Exactly. Thanks, you guys. It's a meso compound. Perfect. So meso compound. There you have it. No exclamation point required. But there you go. So that brings us to section 8.13. This is the last new reaction in chapter 8. And like I was telling my students before I started recording this video, if you want a great kind of way to solve these problems, look at Skill Builder 8.8, okay, in the textbook. And I'm going to use that technique to help you solve these problems. So you don't have to know any mechanism for ozonolysis. So I'll just write it here. No mechanism required. Okay, there's a bit of a mechanism shown in the textbook, but you don't have to draw it. Okay, the idea is this. If you have an alkene, you treat it with ozone, so O3 is ozone, and DMS, that's dimethyl sulfide, okay, which is this compound, CH3, SCH3, it's a gas, okay. You end up breaking that double bond, and then you end up putting an oxygen at each end. So you end up putting an oxygen here and here. So in this case, we end up with a ketone and an aldehyde. So depending on your compound, you might get ketones or aldehydes. Now, ozone, you probably remember this from Gen Chem 1. You would have had to draw the Lewis structure of ozone probably once in your life, okay? Remember, it's a resonance hybrid of 2 contributors, and so they can attack the double bond through this concerted process here, and you end up with something called a molozonide, okay? And then the molozonide undergoes decomposition, and then it reforms to give you something called an ozonide. And then after your reducing agent, which can be DMS, dimethyl sulfide, or a mixture of zinc in water, either one is totally fine. Then you end up, cleaving or forming the two carbonyl compounds, whether they be aldehydes or ketones. Okay, so a question that we like to ask our students sometimes, and there's a few questions in the textbook like this, where it says, well, how would you make this compound? Like, what would the compound you start with be? And before I get into that, I want to take a look at a practice problem, and then we'll backtrack on that one. Okay. So the way that he solves these in the textbook is he said, okay, if you were to treat this compound with ozone followed by DMS, okay, what you do is this, okay? I'm just going to redraw the molecule like this, put my double bond, okay? There we go, and then I'll put this double bond here like this. So he literally says, grab an eraser, okay? Grab an eraser and erase the double bond like this and like this. And then he said, put oxygens on the end of the double bonds like this. And those are the products. Now, it's drawn a little bit ridiculous the way I've drawn it here, but those are the products of the reaction. So you can see that one of them is this compound. This is called acetaldehyde. I'll put in the hydrogen. So that's this compound. Okay, I just redrew it. And the other one, if we count the number of carbons, look, you have 1, 2, 3, 4, 5, 6, 7, 8. So we'll put here 1, 2, 3, 4, 5, 6, 7, 8. And then we have carbonyl groups at carbons 2, 4, and 7. And so there you go. So those are the two products, okay? Give me a thumbs up if that makes some sense to you guys, the way that it's done by erasing the double bond and putting the oxygens on each side. Does anybody follow me on that? Just the rationale? Okay, let me show you another one here. So same thing here. If you were to take this compound, first step, treat it with ozone. Second step, treat it with DMS. DMS. There we go, DMS. Okay, what's it going to look like? So let's redraw the compound. So if we redraw the compound like this, okay, there's our carbon-carbon double bond like that. We're going to grab our eraser and we're going to erase that. And then for the answer, all we have to do is put two oxygens like that. So you end up with two aldehydes here. Now that's drawn kind of ridiculous. A more proper way to draw the compound would be like this. So you have a 5-membered ring, and then you're going to have one of the aldehydes going down, and you're going to have the other aldehyde going down. And if you drew them both going up, that's totally fine too. Okay, so that's how you solve that kind of problem. Now this compound is a meso compound. The meso compound. But anyhow, so if we go back to this problem here, if you're wondering, like where did this compound come from? Well, this one's a little bit more challenging, but let me walk you through it, okay? So there's a couple of possibilities, right? You could either tether these double bonds together like this, or tether these ones together like that. Or if you're wondering, well, why can't I tie, these two together or something like that to come up with the starting material? Remember, this compound here is DMS. When it comes to forming cyclic compounds, remember that in organic chemistry, 5 or 6 membered rings are preferred. Okay, preferred. So what does that mean? It means if I was to tie these two together, okay, to make a ring like that, that would have a total of what? 1, 2, 3, 4, 5, 6 atoms in the ring. And if I was to tie these two together like this, I end up with a total of 1, 2, 3, 4, 5 atoms in the ring. If you tie anything else together, like if you go from here to here, you have 1, 2, 3, 4, 5, 6, but then the other one would have 1, 2, 3, right? So you always end up with some kind of small ring if you put it together any other way. And so that means your bicyclic compound has to have a 6-membered ring, okay? And it's going to be tethered to a 5-membered ring, like that. So now it's just a matter of counting where the double bonds are, and you can see that the double bonds are, oops, that's not very pretty. The double bond, it's worse. The double bond, son of a shit. The double bonds are here, and there's also one here, okay? If you don't believe me, you can just redraw the molecule, okay? You can redraw the molecule like this, okay? Something like that. There's a double bond. There's our double bond. And if you take your eraser and if you erase here and here, okay, and then put your oxygens here and here, you'll see that this is this molecule right here. Okay, if I eliminate these things that I put in here, but you see that those two molecules are identical. Now I'd say that this one is actually kind of complex. The ones that I put in the practice problems in the textbook are not quite this difficult, but yeah, I think it's still a reasonable question. Anyhow, so there you go. So now if we scroll down to the bottom, okay, we go all the way to the bottom down here, okay, we have covered every single reaction in this chapter. So we covered hydrohalogenation. So hydrohalogenation, Markovnikov addition, have to know the mechanism. Anti-Markovnikov addition of HBr with a peroxide, don't need to know the mechanism. Hydration with an acid catalyst, have to know the mechanism. Oxymercuration, demercuration, don't have to know the mechanism, but we did discuss the mercurinium ion. Anti-Markovnikov addition of water, which occurs in a syn fashion. We covered that. We covered hydrogenation today. Then we covered halogenation with bromine or chlorine. We went over the bromonium ion or the chloronium ion. Then we talked about halohydrin formation, and we talked about why the hydroxyl goes to the more substituted carbon and how it's an electronic effect. We talked about anti-dihydroxylation. The first step uses MCPBA or some kind of peroxy acid followed by treatment with aqueous acid. You have to know the mechanism of the second step. We went over that today. Then after that, we looked at syn dihydroxylation, and we looked at a whole plethora of ways of doing that. And the most commonly used way isn't even shown here. The most commonly used way would be to have a catalytic amount of osmium tetroxide, so OSO4, in a catalytic amount, and then NMO as your co-oxidant, but these other ways shown here are fine too. And then the last reaction that we just looked at was ozonolysis, so that's reaction number 10, this one shown here. And yeah, and I told you that the skill builder 8.8 is really handy for that one. So we've literally covered every single section of this chapter now. And so something that I think is a really good idea is to take this sheet, okay, this slide. I would print 6 copies of this slide, okay, and I would fill one out every single day or maybe a couple times a day. I would write down in this one, okay, I would need HX for this one here, okay. For this one, I need HBr and an organic peroxide. For the next one, I'm going to use aqueous acid, right? For the next one, it's going to be oxymercuration, demercuration, okay? Just a way to do that with avoiding a carbocation rearrangement. So H2O followed by sodium borohydride. For the next one, it's going to be an anti-Markovnikov addition of water. So step 1 is going to be borane and THF, followed by hydrogen peroxide and sodium hydroxide. The next one is just a hydrogenation that we went over in gross and dirty detail. So I'll put hydrogen and nickel. It could be palladium or platinum. The next one is a bromination. So for that, we just need Br2. The next one is a halohydrin formation. So we would need bromine, but water as well. The next one is an anti-dihydroxylation. Step 1, MCPBA. Step 2, hydronium. The next one, we learned, again, a plethora of ways of doing a syn dihydroxylation. The best way is to use a catalytic amount of osmium tetroxide and NMO. If you wanted to use one of those other methods, like the sodium sulfite in water, sorry, that's the second step. Getting ahead of myself. Step 1, osmium tetroxide, followed by sodium sulfite in water. That works too. And the last one is ozonolysis. Step 1 is ozone. Step 2 is DMS, or it can be zinc in water. Okay, either one is totally fine. So I would recommend printing this out and doing it over and over and over and over until you have mastered the reactions, because what we've got to be able to do is we've got to be able to predict the products of addition reactions. And so you've got to know the chapter 8 reagents. You have to know all of them. Okay, it says the more familiar you are with mechanisms too, the easier the memorizing the reagents are going to be. So look at the reagents, determine what is going to be added to the carbon-carbon double bond. Is it 2 hydroxyls? Is it 2 bromines? Is it a bromine and a hydroxyl? Is it 2 hydrogens, etc.? Determine regioselectivity. Is it Markovnikov or anti-Markovnikov? Or does it not matter, right? If it's 2 hydrogens, doesn't matter. And then determine the stereospecificity. If it's hydroboration oxidation, it's syn addition. If it's dihydroxylation with MCPBA, it's anti-addition, right? That kind of thing. So now we're going to tie in our content from chapter 7, SN1, SN2, E1, E2. That stuff is never going to go away. And so now we know how to do addition reactions. Yes, we covered that in this chapter, but we also know SN1 and SN2, and we also know elimination reactions like E1 and E2 in gross and dirty detail. So now that you know how to make an alkene from chapter 7, you know how to take that alkene and do all kinds of addition reactions with it. And so let's say we wanted to do a reaction like this. We want to take this unsymmetrical alkene and we want to put the hydroxyl on the most substituted carbon. Well, in this case, you see that it's a Markovnikov addition of water. And if you think about the carbocation that would be formed along the way, you would end up with a tertiary carbocation. And so there's no reason for this to rearrange. And so all you would need in this case is just aqueous acid. You wouldn't have to use oxymercuration, demercuration conditions. You can always write H3O plus. That will work for me. Or you could say a mixture of sulfuric acid and water. Why? Because what's the major component that is existing in solution when you mix sulfuric acid and water? It's hydronium, right? It's H3O plus that is going to predominate because it has a higher pKa than sulfuric acid. What if you have to change the position of a halogen, right? What do you want to move this halogen from this carbon over to this carbon? Well, that's going to require an elimination, right? And this is the Zaitsev product that you want to form here. And so for that, you would use an unhindered base like sodium methoxide, for example. And then you need to do a Markovnikov addition of HBr. So you would just use HBr, right? So you have to know your reactions very, very well to be able to figure out these kind of things. What if you wanted to move a hydroxyl from this carbon down to this carbon? What's that going to require? It's going to require an elimination. You can't just use sulfuric acid and water to do that, because in that case, you put the double bond here, right? In that case, you're going to have to convert the leaving group into a tosylate using tosyl chloride and pyridine, and then you would need a big bulky base to give you the Hoffman alkene. And then if you want to do an anti-Markovnikov addition of water, then you would have to use borane and THF followed by, well, they always put the peroxide first. So hydrogen peroxide and sodium hydroxide, like that. And again, the only way you can do this, right, is by knowing your reactions very, very well. So we've covered Markovnikov, anti-Markovnikov, Hoffman, Zaitsev, all this stuff has been covered in detail. And so if you boil it down, there's been really 10 reactions of alkenes covered in this chapter. And you have to know them, frontwards and backwards. There can be no hesitation about, okay, well, what reaction is this? What is bromination? Otherwise, you'll run out of time, when you're trying to solve those kinds of problems. So make sure you know all of the information on this slide, okay, very quickly, and that you're able to fill this out with relative ease, okay, so that you can, recall those reactions rapidly. So with that in mind, what we're going to do is we're going to take another short break, and we're going to come back and do some synthesis practice. So this is the first problem that I have put in there. So we're these two, and then I have these ones, and then this is just a review of the mechanism. So I'm not going to spend any time on this because I went over it very, in depth with you, which mechanisms are important and which ones aren't. But for this one here, let me just ask you, if I go from here to here in this one, is this a Markovnikov addition of water across that double bond or an anti-Markovnikov addition of water? Is this Markovnikov or anti-Markovnikov, this particular reaction? It is not a trick question, just it's a Markovnikov addition, isn't it? Thanks, Isaac. Yep, absolutely. This is a Markovnikov addition. And so there's two possibilities. Could it be just H3O plus that we're going to use here? Would that work? Or do we have to use oxymercuration, demercuration, meaning step one, mercury 2 acetate in water, followed by sodium borohydride? Okay, which one of these are we going to use? Okay, because only one of them can be the correct answer. If you just used H3O plus, would you get a carbocation rearrangement in this case? Could anybody answer that? If I used H3O plus, would I get a carbocation rearrangement? Thanks, Raul. Absolutely, you totally would, right? So what Raul is saying is he's saying this. Look, let me use my red pen. Come on, pen. There we go. Okay, so what Raul is saying is this. He says, okay, you take this alkene, you treat it with H3O plus, or hydronium molecule, or ion. It's going to do a Markovnikov addition like this, and you're going to end up with, come on, red pen, where are you? You're going to end up with this carbocation like this, right? But that's going to undergo a hydride shift like this to give you a tertiary carbocation. So you're going to end up with this carbocation, and then after nucleophilic attack and proton transfer, the alcohol you would isolate would be this. Okay, we call that 1-ethyl cyclohexanol. Okay, so that means that H3O plus is not going to work in this case. It's a nice idea, but it's not going to work, right? There's the best laid plans of mice and men, right? So we're going to cross off the H3O plus and say that is not going to work, okay? The only way you can get this to work is to use oxymercuration, demercuration, because you are going to avoid the carbocation rearrangement. Now, what about the next one, 8.39? Could anybody give me the reagents to do this one? To do this reaction? What would the reagent be that I would need here? Anybody? Is this a Markovnikov addition or an anti-Markovnikov addition? I mean, what atoms are being added here? Okay, let's take a look. If we look at the carbon in blue, what's attached to it? It's got a methyl group, and then of course the carbon's in the ring, right? It's got the methyl group here. You can see that this carbon still has the methyl group attached to it, and it's also got a chlorine. So we know we're adding a chlorine. And if we look at the other carbon, it's got one hydrogen, which is already here, but it also has another hydrogen. That means we're adding a chlorine and a hydrogen. So that means we need to add what? HCl. Okay, HCl is what we're adding. Is this added in a Markovnikov fashion or anti-Markovnikov? Is this reaction Markovnikov or anti-Markovnikov? Regioselectivity. Yes, it's Markovnikov. Therefore, all we need is HCl. That's the only reagent that we need. So the only reactant that you need in this case is HCl, right? And you could even practice drawing the mechanism. You could say, okay, well, when I have my 1-methyl cyclohexene, what's going to happen is the rich are going to get richer. So that means that my hydrogen is going to be added to this carbon, and then I'm going to end up with a tertiary carbocation like this, and then my chloride, which is a good nucleophile, it's a weak base, but it's a great nucleophile, is going to come in, it's going to do a nucleophilic attack, and I'm going to end up with my product, which has no stereo centers, like that. So there you go. So that's the kind of rationale we want to use with these kinds of problems. So what I'd like you to do is I want to take a short break, and I'd like you to try question 8.42.